All right, so last time I defined a connection on a principal bundle, and today I want to define curvature on a principal bundle, okay? So this is differential geometry. So I'm gonna first review what we did last time, okay? Let G be a V group. And I, a principal G bundle. Now a connection on P it could be one or two things, right? So it's something that allows you to differentiate sections. And so it's a way of comparing two different fibers. And that means you want a horizontal distribution, okay? So it is a C infinity right invariant horizontal distribution. That means at each point P of big P, you have a complementary subspace of the tangent space to the vertical space, okay? So that's one way to describe a connection, or equivalently, what's another way to describe a connection? Using differential forms. Yeah. It's a G value 1 form on P. Okay. So such that okay, let's call it omega. So for A in G, omega at P applied to the fundamental vector field associated to A is A, and it's right equivariant. So Rg star of omega is at G inverse omega. Okay? Okay, so last time we showed that these two characterizations of a connection are equivalent. And now I want to give an example of a connection on the product bundle. Okay. Using the Moreau-Cartan form. So the Moreau-Cartan form on a V group G is the unique left invariant G valued one form theta on G such that at the identity it is the identity. So theta E of XE is XE for XE in the Lie algebra, which is the tangent space at the identity. Okay? So there is a unique G-value 1 form of G. Such that it's the identity at the identity. And theta satisfies the Morrow-Cartan equation. Which is d theta plus 1/2 bracket theta is 0. Okay? Okay, so now suppose we look at the product bundle. So on the product bundle, there are two projections, pi 1 and pi 2. And pi 1 gives you a principal G bundle. Now pi 2 allows you to pull back the Morrow-Cartan form. So let omega be the pullback of the Morrow-Cartan form. Okay, so then this is a G-value 1 form. On M cross G. And in one of the homework problems, I ask you to show that it is a connection on the trivial bundle. So in other words, it satisfies these two properties of a connection. So omega equals pi 2 star theta is a connection on the trivial bundle. Okay. And if you pull back the Morrow-Cartan equation, so because pullback commutes with D in the bracket, you get, so you'll get d omega plus 1/2 omega is 0. Okay. Now this is a G-value 2 form on the product bundle. And so we can use it, as a measure of the deviation of the connection from the Morrow-Cartan connection. So we define it to be the curvature. The G-valued 2 form, omega equals d omega plus 1/2 bracket omega on a principal bundle is called the connection. It is called the curvature of the connection. Okay. And for the Moral-Cartan connection is 0. So it's a measure of how different your connection is different from the Moral-Cartan connection. It's a measure of the deviation of omega from the Moral-Cartan connection. Okay. Yeah. Now, you might wonder why it's called the curvature. I mean, it's actually related to, the way, say, a surface curves. But that takes quite a bit of time to explain. So, that's what I tried to do in the course on differential geometry. Why this is called the curvature. But here, we just have to assume, that it is the curvature. And so both the connection and the curvature can be written with respect to a basis. So with respect to a basis x1 to xn for the Lie algebra, omega is going to be a linear combination of the xk's. Okay. So omega in the linear combination would be, would have R value coefficients. So, and big omega is a linear combination of the xk's. So where omega k and big omega k are R-valued forms in P. Okay. And yeah, so okay, now we can write the definition of the curvature in terms of omega k, and it's going to be d little omega k plus 1/2 well, let me see. Let me write down the bases as well. D omega k xk plus 1/2 bracket sum of, say, omega let's see, I, xi, and omega j xj, right? Okay? Oh yeah, sorry. This should be J. Yeah. Uh-huh. And then you expand that out. Omega I wedge omega J. And then you have bracket xi xj. Okay, bracket xi xj is cijk xk. And now if you compare the coefficients of xk, so you get omega k is d little omega k plus 1/2 the sum of cijk omega I wedge omega j over Oj. Okay? Now, okay, so this is the definition of the curvature omega. It's also called the second structural equation. Okay, and now, okay, so yeah, so this gives you d omega, d little omega in terms of big omega and little omega, okay? And then now there's another equation. It's d of the curvature. What is d of the curvature? Right? So, theorem. This is called Bianchi's second identity. See, there is a first structural equation, but that is for the principal bundle, associated to the tangent bundle. And there's Bianchi's first identity, which is also for a principal bundle associated to the tangent bundle. But we don't need that, so we'll just prove the second Bianchi's identity. Okay, it says d of the curvature is bracket of the curvature with the connection. Yeah. Okay, so let's prove this. Yeah, so omega is d omega plus 1/2 omega omega. Okay, and therefore d omega is d square omega plus 1/2. Okay, d omega omega. Okay, and then since omega is a one form, you have minus 1/2 omega d omega. Okay, and okay, now this first term is 0. Now Now d omega is big omega minus 1/2 bracket omega omega. Oh, let me see. Yeah, let's first simplify this. Okay, how are these two related? If you switch these two, this is a 2 form, this is a 1 form. So if you switch those two, there's a sign, right? And the sign is -1 to the degree of this times the degree of that. So the sign that comes from switching these two is +1. Okay? However, you have a Lie bracket there, so when you switch the two, there's a -1. Therefore, this is the negative of this, and so these two terms combine to give you this. So because omega d omega is minus d omega omega. And then d omega is the curvature minus 1/2 bracket omega omega. Okay? So this is from the definition of curvature. And so this gives you curvature bracket omega, and then minus 1/2 bracket bracket omega omega. Now, in one of the homework problems, I ask you to show that if tau is a g-valued 1 form on P, then bracket bracket tau omega tau is 0. Okay? So this is essentially the Jacobi identity for a Lie bracket. Okay? And so therefore, d omega is bracket big omega little omega. Yeah. Okay. Now, the curvature has some other properties. Okay, so yeah. So the first property that it's horizontal. Okay. Now, what does it mean for a form to be horizontal? yeah, if one of the argument is vertical, then you get 0. Okay? It vanishes on vertical vectors, i.e., so if you apply a vertical vector to omega, you get 0 for any vertical vector. And a vertical vector is always of this form, right? It's associated to some A in the V algebra, okay? So it's horizontal, and then it's right equivariant. Okay? If you right translate by G, you end up multiplying by add G inverse. Okay. Okay. Now, all right. The first property takes a little bit of work. Well, you know, you have to use the definition of the curvature omega, and you apply it to a vertical vector, okay? And then you need another argument. So that second argument, okay. Yeah, it turns out that curvature depends only on the horizontal component. So in other words, there's a formula that omega applied to xp,yp is equal to v omega p applied to the horizontal component. You see, once you have a connection, then you can decompose any vector, any tangent vector, into a vertical component and a horizontal component. Okay? So where xp equals vxp plus hxp is the decomposition of xp into vertical and horizontal components. Okay. So if you can prove this formula, then it will show that the curvature is horizontal. Because if you have a vertical vector, then its horizontal component is 0. Okay? So 1 follows from 3, and to prove 3, because omega is linear in the arguments, there are several cases. You prove it for vertical vectors and for horizontal vectors. Okay? So there are 3 different cases. One is when both are vertical. The second case is when one is vertical, one is horizontal. The third case is when both are horizontal. Okay? 3. Now, it takes a while to prove that because there are 3 different cases. And so it's not important for us to prove it, okay? If you want to see the proof, I have sent you a chapter from my book on differential geometry, and the proof is there. So we're just gonna assume this result. So the proof is, this is theorem 30.4. And then once you have 3, then 1 follows, right? Okay. And 2, it's because little omega satisfies the same property. So you just apply it to the definition. Okay. Okay. Yeah. Okay. So now we have the background in differential geometry. Okay. So I want to go back to a manifold on which there's a group action. Okay. And I want to look at the round complex of C infinity forms on this manifold. Now it's a differential complex and it's an algebra. Okay. So it's a differential graded algebra. Suppose a Lie group T acts on a C infinity manifold M. Okay. Then the C infinity forms on M. It has a differential, it's graded, and it's an algebra. So it is a differential graded algebra. Well, that doesn't take into account the group action. Right? For any manifold, the C infinity forms is a differential graded algebra. Okay? Now the group action gives this algebra some additional structure. So on this differential graded algebra, we can define 2 actions of the Lie algebra. Okay, we can define interior multiplication IA of tau to be, well, this A gives you a fundamental vector field, A bar, so you can take the interior multiplication of tau with respect to A bar, and then you can take the Lie derivative. Okay, so for A in G. So you can define these two actions of the Lie algebra on omega n. And then we can also define an action of G. Okay. So for G in G, we define right translation. Okay, so we define G dot tau to be right translation. And now, and then we have this property. So LA, the Lie derivative satisfies Cartan's homotopy formula. Okay. So LA is equal to, let's see, do you remember this formula? This is, LA can be written in terms of interior multiplication and the exterior derivative. LA is equal to B IA plus IAB. Okay. This is very easy to show because both sides are derivations. Okay. So you only need to check it on the generators on one forms. If it's true for one forms, then it's going to be true for all forms, okay? Because both sides are derivations. Now, a differential gradient algebra with these three actions is called a G differential gradient algebra. Okay? So what this says is that the de Rham complex of a G manifold has this algebraic structure, okay, of a G differential gradient algebra. Yeah. A differential gradient algebra with the actions 1, 2, 3 satisfying let's call Cartan's formula 4. Is called G differential gradient algebra. Right? So the first example is that any manifold with a group action will have a Dirac complex that's a G differential gradient algebra. If M is a G manifold, then omega M is a G differential gradient algebra. Okay? Okay. I want to give you another example. And it's called the Weil algebra. Okay. Now the Weil algebra is constructed out of the Lie algebra. Okay. Yeah, so suppose, now let's see. Yeah, suppose you have a principal bundle with a connection then the Weil algebra is the exterior algebra of G dual tensor with the symmetric algebra of G dual. So this makes it into a graded algebra, but I need to define a differential on it, and then I need to define the action of the Lie algebra and the Lie group on it. Okay? And in order to define them, you see, I want to first define the Weil map. Okay? So the Weil map is going to go from the Weil algebra to the Dirac complex of forms on P, and it will be a morphism of G differential gradient algebras. So it will preserve the actions, okay, and it will preserve the differential. And that will tell us how to define the differential and the action, okay? So now, okay. So suppose you are given an element in the dual. In the point P in P. Now, because you have a connection omega P takes a tangent vector to G. And you can follow it by alpha. So then you get a linear map from the tangent vector to R. That means the composition is an R value 1 form. On P. Okay, as P varies over P. Okay, so this gives a map F from G dual to the one forms on P, where F of alpha is alpha composed with omega. And then you can extend it. Okay. So we can extend F to the exterior algebra as an algebra homomorphism. Okay? So in other words, i.e., if, say, x1 to xn is a basis for G, and alpha 1 to alpha 1n is the dual basis, then the exterior algebra, it's generated by alpha 1 to alpha n, and we define f of alpha 1 which alpha n. These will generate the exterior algebra, and you define this to be f of alpha 1 which of alpha n. Okay? So this is the V map on the exterior algebra. Okay? This gives the V map. F on the exterior algebra. Now it's a V map, so I probably should call it W. But I don't call it W, well, because W looks too much like omega, the connection, okay? So I call it F, yeah. All right, so let's take a 10-minute break, and then we will continue at 1:20.